Okay, this is part 6 of my Linux CNC how tutorial. In this one, we're going to set up ohmic probing so we can use the G38 commands to find out where the workpiece is in relation to our Z-axis on this CNC plasma table. Now, ohmic probing is very simple, very easy to set up. Basically, all you're doing is dropping the torch head down until it makes electrical contact with the work, and then marking that spot as Z equals 0. The best thing is, all it takes to set up is a pair of $1 relays, a few feet of wire, and a few lines of code in your HAL configuration files. So very, very simple, very effective, very efficient, and really something you must have if you're going to have a CNC plasma cutter. Even more so than a torch height controller, the ohmic sensing before every cut will at least get you in the right ballpark on your Z heights. And it's especially important for a plasma cutter because these machines are picky about their Z. You know, if you're too far away, the arc won't transfer, or if you're too close, it also won't transfer. Kerfs will be too wide or too narrow and sloped or whatever. The Z height's very important, and the ohmic sensing gets you the majority of the way there. And even though we're talking about this on a plasma cutter, the same things still do apply to other tools, of course. In fact, with like a mill, ohmic sensing can still be useful just to do tool offsets, right? So you put a new drill into your mill, then you do a ohmic touch off to see how much drill is sticking out, and with that you can determine how far down you need to go when drilling your holes. Even better, if you're drilling a project with like 100 holes in it and you want to do that unattended, you can even use probing to see how long the drill bit is between each drill, and that way you can detect when a drill breaks, and if it breaks, so you can stop the process there and not, scrap your work entirely. So tons of different ways you can use this. In fact, oh man, I saw this really great video maybe 2 or 3 months ago of a guy who used a dial indicating probe on his Linux CNC mill and then hooked up that manual probe to a CNC. And he did that by putting a webcam in front of the dial and then processing the image from that webcam with a user space HAL component he wrote. And then when the dial hit 0, he triggered the probe in HAL. Really great stuff. I'll see if I can find that video, put the link below. And even better, he took the code he wrote for that and put it somewhere up on GitHub. So again, I'll look for that and put links below. But yeah, let's take a look at how the probing works on my setup now. And then we'll look at the wiring and then the HAL after that. So I've got my handy dandy Xbox controller here, and I set up a shortcut on it that'll run my probing routine. So first there's a fast probe. When it gets near, there's a slow probe. And it touches, backs off, that's Z equals 0. So now say I were to move across the table and be doing a cut somewhere else, and because these plates are always sloped. In fact, you can probably see just how much that's lifted up there. Because the plates are sloped, the Z height changes from spot to spot. So if we went down elsewhere, and now the Z was that much higher, and I probe again, it'll still pick that up before the next cut. So really helpful, even more important than having a THC. So now, let's go on to the wiring and the HAL. Now please pardon the mess over here on the wiring board. Well, I might have been working this machine for about a year now. It's all still kind of a prototype setup, just because hobbies take forever. But I will try to point out the important part in this whole, mess of wires. So right here on pin 11 on the input side, we've got this little wire, and it makes its way all the way up to the shield on the torch head right there. So coming over here, see the wire comes down and it connects to this little brass spring clip I bent out of some old scrap I laying around to press up against the shielding cap. Now this cap is typically isolated from everything else by the ceramic coupling nut. So this is just hooked up to the wire, back to the parallel port breakout pin, parallel port board breakout, and back to the thing over there, and nothing else. So when this touches down, it then connects to the work clamp, to the work lead, to this junction block, then back to this little wire here, which eventually goes back to ground on that breakout board. Now this junction block is simply because the work clamp that came with the plasma cutter is a little bit obnoxious. It's nice, but it's also just, it's enormous, and it always gets in the way when you're trying to cut stuff. So I made this little junction block. That way the big clamp stays out of the way. I can use a low profile clamp, and also make sure that whenever that clamp is hooked to the work, that this signal wire for the ground is also hooked to the work. So now we have the input pin that's normally pulled high to 5 volts, and we touch that down, it gets pulled to ground through the whole connection, and pulling it low then signals the probe on Linux CNC's HAL readings. Now, I did also mention there are 2 relays in the setup. So what's the deal with that? Well, when we're plasma cutting, that plasma comes out of the torch right here, right where the shield is and where this signal wire is. And it goes to the ground lead over by where that signal wire is. So plasma cutters get up to like 300 volts DC. And that can put 300 volts DC up that little wire back down to your breakout board. And that is no bueno, right? So what we do to fix that is take 2 little relays, and in my case, we just hot snot them to the side of the CNC machine right here, and we break the connection between the parallel port breakout board and the stuff over there by these relays. So we got the wire from pin 11. It comes up here, and it's broken, and it comes to this green wire. So the student among you might have noticed this wire was originally white and green, and over the torch it was solid green. That's where it makes that transition there. And then the lower relay is what breaks the ground connection. So you break it on both sides, just so there's no risk of a high voltage current ever making its way back to the breakout board, which would not be able to handle that current. Simple, right? And now this setup of relays are both triggered by one output pin, by pin 17. So this little white wire comes down and around to, this really janky twisted connection there. Ooh, I should probably fix that one. Anyway, and then that is what switches these 2 relays to enable and disable the probe. So if I grab the controller one more time, when I start the probing routine, those turn on, that touches down, and they turn off. And that way it keeps the whole setup, as safe as this all can be. Anyway, now we're on to HAL and the Linux side of things. As usual, let's begin by looking at the Git history of all the files in this project, which of course you can also find up on GitHub. So I just demoed the stuff here at part 6, and to get there from part 5, we had 1, 2, 3, 4, 5 steps. In the first step, I had a brand new HAL file, 30-thc.hal. I did name it THC, though there's nothing about the TorchEye controller in there. Patience, that's part 7, that's coming up. And then of course, every time you add a new HAL file, you have to update your INI to let it know about that file. So just one small change here, adding a new HAL file to the list. So since the thc.hal is all brand new, let's pop that open in a regular editor, get a better look at it. And here we go. Everything here should look pretty familiar. If it doesn't, you really ought to go back and watch the first 5 videos in this series. I know it's a lot of content, but there's a lot to learn with HAL, and beginning at the basics and building up is the best way to learn. If you've gotten this far, this should all be pretty simple, and we can go through it rather quickly and easily. I just can't put all that content into each and every video, right? So the key part here is down at the bottom, we are putting a signal at the motion.probe input pin. And as you probably know, if you check the man page for motion, you can find the probe input, and there it is. It's an input boolean, and it is what controls the G38.x commands. Now it says .x because there's like 4 or 5 of these commands for like probing forward and backward and signaling on error or not signaling on error. There's a few of them, but they're all controlled by this one HAL pin. And we are feeding that off of an OR2 component. We've seen that before. And this OR2 is comprised of 2 things, the parallel port pin 11 and the Xbox Y button. Now, what's the Y button for? Well, sometimes you cut material that is either painted or just very rusty, and in either case, not electrically conductive. So if the surface is painted, your ohmic sensing will not work, right? The best thing to do would be clean it off so it does work, or to have a backup method, right? So the best backup method is a sliding torch head, otherwise called like a floating torch. so that when it touches down, it moves up a slide until it bumps against a physical micro switch, and then that can trip and act as a backup probe. I don't have a sliding torch head though, so instead I use the Xbox button with the Y, and when the thing gets close, I hit Y, and it's good enough, you know, for the amount of material I cut and how rarely I see painted or rusty stuff. This, you know, a little bit of babysitting works well enough for me. I think this connection here on the parallel port pin is the first time we've seen an input pin be used. So in this case, using the in-not variant of that pin is what makes it trigger when you pull the pin to ground. So typically it's drawing it high, and then when it touches the ground, that pulls it low, and that's what sends the true to this OR, so it eventually boils down to the motion.probe input. Now, whether or not you need like pull up or pull down resistors or capacitors or whatever on your breakout board really depends on how the board is designed. For me, as I showed with my Wantai Motors brand board I got off eBay forever ago, that one has like pull-up resistors built in, so all I need is the wire coming on pin 11 and then this in-not on the HAL here, so it triggers when it gets grounded. Now for the safety setup on the relays, all we've got there is the motion digital out pin that we can now control with what, M62, 63, 64, 65. That goes to our power port pin 17, and then we do the invert on that, because as I've said a dozen times before, my relays trigger when they get pulled low. So this makes those relays get pulled low when this signal here goes to true by running the G-code command. In theory, this would be enough for us to do probing, but it requires a lot of song and dance, right? First turning on pin 17, then doing the fast probe, the slow probe, the pullback probe, and then turning pin 17 off with all the error handling in there. It's a lot. So instead, let's put that in a subroutine to make things a little bit cleaner. And you'll see in the next commit, that is exactly what I did with the new probe.ngc. I added a few more things in here too, so let's go over them first really quick. So in the INI file, I added a new MDI command shortcut for actually calling this probe subroutine. And then in the post-GUI HAL file, I hooked up the Xbox right on the D-pad to that MDI command. So you would have seen this in video 5 when I went over all the Xbox setups, and that's why I have these shortcuts right at my fingertips. Then in the 30-thc.hal, I added one new connection, adding the ohmic found signal to a motion.digital in pin. Now, what's that about, right? It's another way to check that the probe is switched or not, and we'll get to that in a moment when we look at the G-code. And then last but not least, in the steppers file, way back when, generated by the StepConf wizard, there were a couple of signals that I didn't know I had turned on, wiring up digital input pins already, so I just took those out because whoopsie. But yeah, ignoring that, let's go look at the probe file, right up personal. So check this one out. And then here we go. First off, we want to activate the relays we use for probing. So those two I had glued to the side of the CNC machine, they're now flipped on, so that way the whole probe circuit can be connected when the torch head touches down. And these are available as P1 because I hooked them up to motion.pinin-01. Since pinin -00 was already taken up by the crosshairs that we added to the machine way back in video 3. So that's already taken, so now we've moved on to using input pin -01 and P1 here in the M-code command. Then we sleep for a moment just to make sure those relays do in fact connect, and then we save our current Z location using the built-in variable _Z that we've seen before, and we're going to use this current Z location at a few points in the rest of the subroutine. Now here is where we use the motion input pin that I just hooked up. So that ohmic found signal goes to two things. Firstly, to the motion.probe input, and also to the motion.input pin for input pin P0 different from this output pin P1. This is an input pin used with M66 and P0. And what we're doing here is we're checking to see if the relay connection for grounding is already made before we ever do probing. This can happen when slag gets knocked back upward from the torch and lodges itself between the nozzle and the shield on the torch head. As I mentioned, that shield is typically isolated from everything, but if you get slag blown back up in there, it can connect to the nozzle, which then effectively goes all the way back through the ground clamp and then to that little wire we have going back to the ground on the parallel port breakout board, and that can trip your relay, making the machine think the relay's touched down the moment you run your M38 command or G38 command. So we check that first, and if this returns true, right, we do an N66 on pin 0 with an immediate return, I think this one is, yeah. And then we check the built-in variable for the status of that, and if it's true, found, then we display the message to check our torch, and we do this little song and dance that lifts the torch up, pauses, lets us clear it and check it, and then carry on. So G28 is a command you can use to move to the machine 0. So the way it works is you pass it a position, it will move to that position, and then it will move to the absolute 0 for that axis. Now with my Z, the 0 is at the very top, and I drop it down when I'm cutting into the negative space, and then 0 it out again using G92. So what this effectively does is move it to where the torch already is, so no move at all, and then it lifts the torch up all the way to the max of the Z, so you have the easiest access to unscrew that shield, knock out any shmoo, and then unpause it with the play button, because then 0 doesn't pause, you hit play to resume, then it moves back down to where it used to be, and carries on. The probing itself happens in a couple of stages. So first off, we open up this if block, and then if we are currently high, right, if we're greater than 0.2 inches from what we think the surface is, we will do a G38 at a fast speed. So G38.3 does a probe down, and if it doesn't connect, it does not raise an error. It lets you continue on with the program. So we probe down to 0.2 inches above where we think the surface is at 99 inches a minute. It doesn't actually do 99 inches a minute, it just goes basically at the max speed, because you have to provide some value for F. So F99 is, faster than any machine will reasonably go. Then we find that, we're going to mark that spot where we did touch as 0, move back up a little bit, and then do a slow probe. That's because if you touch the probe at max speed, then you probably ran into it with a little bit of gusto, went a bit beyond what the bottom really is. So we're going to back off and then do it again in a slow style. If you've seen a 3D printer with a self-leveling bed, this is also typically the way they do it. They'll probe fast and then they'll probe back down again, nice and slow. Now, of course, if we're already near where we think the surface is, then we will just begin by doing a slow probe. This slow probe only goes to negative 0.2 inches below where we think the surface is. That's because, again, I don't have a floating torch head or even a magnetic disconnect, a magnetic breakaway torch. So as a safety, I only probe that narrow range, which for most applications should be good enough, right? Your plate should be level enough that it will fit somewhere in that range, but it does let me, compensate for when there is, a quarter inch or so of slope between one end of the table and the other. This also comes into play on the first probe of a job. If you've forgotten to hook the work clamp up, right, then because that work clamp is not connected, it will fail the probe, and it will just keep going down until it hits material, and it will push a little bit further, but because it's only doing -0.2 inches, it won't go so hard that it really, botches up the machine. And then seeing that it fails also ends up warning you right away that, oh, you forgot to connect the work clamp, so stop the machine, connect the clamp, and then restart the program from the beginning. Then carrying on, if this probe failed, then we have some sort of stranger error, really don't know what it is, so we say if the probe result does not equal 1, it's not successful, we lift the torch up all the way, same way as last time, give this message, hey, the probe failed, and then we pause. From there, I'm probably going to take some time to debug the issue and just mark the line of G-code I'm currently at, and then restart the whole program from there once I fixed whatever it was. Then, if that probe did make contact, which it basically always should, granted, like assuming that you've connected up the clamps and the material isn't rusty or painted or whatever, then we're going to lift up slowly using a G38.5 command. And we're going to lift up just a little bit, nice and slow, until we break contact, and then that will be where we mark our Z equals 0. And of course, for this one, we mark the Z position to move to as the original starting position from the very top of our subroutine. And what that does is it means that we have a valid position to move with this probe, because you have to provide it a Z position, and it has to be one that's within the machine limits. So as a simple hack to make sure this move is safe and valid, we just use the starting position, even though it will stop the probe the moment it breaks contact with the material, which is usually, just a little fraction of an inch. Once we break that contact, we can set our new Z equals 0, disable the probing relays, and then call that the end of the subroutine. The next thing we need is a subroutine for cutting. And sure enough, look at my next commit, that's exactly what I added, a new cut.ngc file. So let's take a look at that one. So we need to do a, git checkout for the next commit. And FYI, this get next is an alias of mine for finding the child commit from where you are already. In fact, if I do a git config get alias.next, that is a magic command that will tell you what your child commit is when you only have one child. It's some Git magic. You might find it handy if you're a programmer. Otherwise, you can skip that part. But anyway, now we've moved forward in the Git history, and we can see the cut.ngc file is now there. So let's take a look at what it contains. The most interesting part about this subroutine is that it takes arguments. So the call style for it is a little bit different. It's call with the O and the subroutine name, and then the arguments come here in brackets, one after the other. And then it makes them available in the number 1, number 2, number 3, etc. Variables. I think all the way up to number 30 is the max that you can have. And of course, the whole number variable thing and the brackets around the arguments, it's all just archaic gobbledygook. It's part of G-code being an old and conventional language. But that's the way it works, and it does indeed work. And we take these variables then and shove them into new variables with names that are human-friendly so you can actually tell what the fuck is going on. All right? Now the first thing we do in this routine after setting those variables is make sure the relays for that probe is off. That way, if I ever set them on manually for some reason, like not using the probe routine, but I maybe botched up and mistakenly did an M64 P1 and turned it on, this will make sure that they are off before I even begin the Pierce routine for the plasma cutter. Now there are other ways you can make sure they're off as well. Say you can take the spindle on signal and then check that with, an XOR before you feed that to the parallel port out. Right before you feed the pin 17, take the motion, output pin -01 XOR the spindle on signal, and then feed that to the parallel port. The problem I see with that is that then you're relying on the switches for the relay turning faster than the switches for the plasma cutter, right? Because they will turn off the moment the plasma cutter turns on. And rather than deal with that timing there and having to worry about the relays maybe being slower than the plasma cutter, I just make sure I do that right here, right now, and that way it's fully off before the plasma cutter gets close to running. There's a million ways to skin that cat. You can do it how you want. I think that having it here in the G-code is enough safety for me. Anyway, after we turn that off, we move on to a typical Pierce routine. You move to your Pierce height, you wait a moment, you start the plasma torch, then you wait for the delay on that, then you drop down to your cut height, and then you set your feed rate for you to begin moving with the G1 commands to actually cut out the shape you want to cut. Now, I'm not waiting on a arc OK signal in this code. There's a a set of pins for that on my plasma torch to read the RQK signal from the hypertherm, but I haven't yet wired them up to the plasma cutter, and I've found that really I don't need that. If I just wait for the amount of time listed in the hypertherm manual, then my arc pretty much connects every single time. I don't need to wait for the RQK from that torch to know that's connected, because it's a very, very, very reliable machine, and a simple delay has worked well enough so far. And then I want to point out that when you get to the end of this subroutine, you currently have M3 active, right? Your torch is on and ready to cut. So you want to make sure that the next line of your G-code is doing some G1 commands to move around and begin cutting out your shapes, because the torch is running right now. Likewise, I have not put this on a shortcut because I don't ever want to bump this by mistake on my Xbox controller, right? I'm not going to be doing freehand cutting at any point in time. So this one only gets called from a G-code program, or possibly from the MDI console if I have a couple lines of G-code already primed, ready to go. But I'm not going to ever call this freehand, so we will not set this up with an MDI command shortcut in the INI and the PostGUI HAL. Moving on to the next commit, let's see. We get a little bit fancier still by building on top of that PyVCP panel we did before. So go back to our XML, and where we used to have just the check button for the crosshairs, we now add a new LED that displays when you've made ohmic contact. And to make that work, we just put the XML for an LED in here. We give it a label of, let's see, yeah, LED ohmic. And then over here in the PostGUI HAL, we feed that ohmic found signal onto PyVCP.LED ohmic. And that's all you need for a new signal or new display on your PyVCP panel. And last but not least, we've got one thing that gets, this one's a little bit complex, but I put this in here kind of as an example of what you can do in HAL and some of the more complex things you might want to tackle. So let's pop this open and I'll explain. So I do git checkout for the last commit in this part 6. Let's see, configs, HAL, and view 30, and here we are. All of this gives us a pretty good functioning machine, but it does have one catch. And that's that the Xbox button we set up as our ohmic probing backup is active all the time. That means if you bump it during a jog or during a job, you're going to get a probe tripped error, and that can interrupt what you're doing, right? So we could fix this by, say, combining the Xbox Y signal with the enable probe signal using an AND2, and only consider the output of that then if both those things are active, right? So only listen to the Xbox Y if you're also having the probe relays turned on. But you might not want to do it that way either, because then, whenever the probe's on, the Y button works too. And you might want to have those probe relays turned on during rapids across the machine, not only when probing. Now, why is that? Well, because then you get collision detection for free. When you're cutting, if a piece you're cutting out tips up as opposed to dropping all the way down fully into the waterbed, your torch might run into that later on in the program. And if your probe relays are turned on, when you run into that, it will raise a probe hit error, and then it will pause and wait for you to check it and make sure it's okay before you move on. Otherwise, if you run into stuff with your torch like that, you can drop steps, and then these drop steps will throw off the rest of your work and scrap the part. So collision detection is generally seen as a positive thing. I'm not personally making use of it yet, but for the sake of example, we're going to do the technically correct thing and enable the Xbox Y button only while we are actively probing, while we're in the middle of a G38 command. It is more involved, but it lets me show you some stuff about type conversion and things and get to a bit more complex type HAL that you aren't going to see otherwise. So the main thing we've got here is way down at this part. We have this motion type pin right here, and looking at the man page for that, we can see that it puts out an integer value depending on the type of motion you're currently doing, where number 5 is for probing. So the end result of what we want to do here is check and see if this value is 5, and if so, we'll take the input of the Xbox Y button as a backup for the ohmic sensing, and if it's not 5, we'll simply ignore it whenever you hit the Y button. That way you don't mistakenly trip the probe while you're doing a rapid or at any other point in your program, okay? Now the whole, I don't know, song and dance to do this check and the conversion to eventually get to the is probing flag here is a little bit complicated, but I'm going to try to walk you through it as best I can, just as an example, again, of the most complicated HAL you're going to possibly run into, and mostly because these conversion components are kind of special and they don't appear in the docs. So I want to show you how I found out about these things and how you can kind of stumble through this Linux CNC, some of these finer parts to find the things you might need that might not be right at your fingertips, right? To help you learn how to debug and troubleshoot more complicated things on your own. So, I guess the main way we're going to be doing this equality between the motion type is by using a bitwise XOR, right? So we got this motion type, we have this 5. So we feed this 5 into bitwise input 0, and we feed the motion type eventually down here into bitwise 1. And we read out of that the XOR value. We talked about ORs, we talked about ANDs. I don't think we talked about XOR yet. So it's like an OR, but it's the exclusive OR. It's basically a special case in which it's true if either one but not both inputs is true. So an example is probably the best way to go over that. So this is the number 5 in binary, and this is the number 7 in binary. So typical OR, you go down the line and say, here's a 1, here's a 1, and here's a 1. So it's just 1, 1, 1, that gives you 7. But with an XOR, you would say, here's a 1 and a 1, so that will actually give us 0, because it's exclusive OR. Here's a 0 and a 1, that's a 1. Here's a 1 and a 1, that's also a 0. And that ends up giving us 2 in decimal, if you do that conversion there. So it's a slightly different variant of OR. And the tricky thing about that is if the numbers are the same, then the XOR always comes down to 0, because you have a 1 and a 1, so they cancel out, become a 0. A 0 and a 0 stays a 0. A 1 and a 1 becomes a 0. So the XOR ends up being a way you can check if two numbers are equivalent. And then if they are, you get 0. So we've got this bitwise XOR output, and we feed that into a NOT that turns it into a true when these two are equal, right? Equal gives a 0, then the NOT flips it around, so we get a true, and that then becomes our is probing signal here. And we can take that is probing and then feed that into 1/2 an AND, take the Xbox Y, feed that into 1/2 an AND, and then the output of that becomes the signal for our backup probe, right? For whether or not we want to actually listen to that Xbox Y. Now, the tricky part of all these different connections here is that they're not the right types exactly. If you might have noticed here, this gives us an integer, and it's a signed integer. All we've dealt with so far have been booleans, right? So single bits, either 0 or 1, true or false, very, very simple. When it comes to more complicated types, whether they're integers, right? You have signed and unsigned, and then you have floating point numbers, which are entirely different. And this all gets to more, I guess, the nitty-gritty programming details of working in C and stuff like that. But basically, this gives out a number, and this number can theoretically contain values from -2 to 31. That's like 2 billion, to +2 to 31. That's, positive 2 billion. And the bitwise operator we want to use ends up actually taking a unsigned integer. So that's between 0 and 4 billion. So we need to change that type over to let the bitwise operator take it. Now the tricky thing about this, like I said, is that it's not anywhere in the docs. So how the hell did I find out that we have these type conversions available to us? Well, that's where a bit of Linux knowledge comes into play. So basically, we know that there's an AND2 component. We use AND2 all the time. So given that we're on Linux, we can easily find files named AND2 using the locate command. So check that out, and it gives us a pretty small list of things that match AND2, right? Here's AND2.conf, here's command2, right? But looking down the list, we see, oh, here's a thing called real-time modules Linux CNC AND2. That sounds like a real-time HAL module for Linux CNC, right? So if we go to that same directory And we just bumble along to user real-time modules, Linux CNC, and take a look in here. Well, shit, here are all the components we have at our disposal, the things that are actually installed on our system. So right here, we've got the N2, somewhere over here, here's our R2, here's our logic, and here's a whole bunch of stuff we haven't even touched on yet. So if it's not in the docs, you're gonna see it somewhere in the list right here. And I notice we have all these different conversion ones, right? So I'm taking a look at the man page for, let's see, man conv S32 to U32. And it basically just has an input and output, and it takes the signed integer and spits out an unsigned integer. It doesn't really change anything unless your value is negative, right? If the value is 0 or positive, then nothing changes. It just changes the type. It lets Linux know that, hey, I can treat this as an unsigned integer and it's okay. But of course, you have a negative, then it gets kind of hairy, and that's when this bit here flips and you know it's out of range. But we don't worry about that because our motion type only puts out these 0 to positive values. It really doesn't even need the negative range. But anyway, let's see. So yeah, that's how we do that conversion there. And that's how I found out about these things. So if you want to know more about what components are available, check the man page for each of these and you can get a better description. Or you can also use, I guess, the what is command is another handy one to get basically the short version of the man page. It's like what is U32, S32, U32, gives you the first line of it saying convert a value from one to the other. Now you might find some of the HAL files here do have really kind of crappy man pages, right? Like I said, the documentation here is generally pretty good, but there are spots that are patchy. So in that case, you might look at the source code itself if you really want to find out exactly what it does. So you might have noticed up here where I did the locate file, there's this an2.comp. Well, what is that, right? Well, I have a checkout of the whole Git project for Linux CNC on my computer here, just to have the source code at my fingertips if I happen to need it. And this is the file that defines the an2. In fact, we won't bother looking at that. We'll look at another component in part 8, so we'll save that for later. But basically, these things are not that complicated on the inside for the most part, and if you can write code for Arduinos, like that really basic C, you can write some pretty basic components too that will do this math for you. So rather than doing this whole song and dance, you can write a component that takes care of it for you. But basically, since the bitwise out, bitwise in needs to be unsigned int 32, we convert that here, then we feed it in. And then the output of it is also an unsigned int 32. So then we convert that to a bit. And then we flip that bit, taking the output of it, and we flip it using the not, and then feed that to is probing, taking that not output and turning that into the and. And then after all that, we have our final signal for this backup probe to let us know whether we should use the Xbox Y button or not when we just hit it in the middle of a program. Whew! And that is probably the most painful bit of HAL you're ever going to see out of me. But it does work, and it shows you how much you can do without even writing your own components. Any crazier than that, though, and I would probably write the component that would handle this conversion in just C code. Like I said, it's basically the same thing as Arduino programming, and we'll look at that later. And a few things like this you could do in a single line of C. But yeah, for that now, our Xbox button is disabled when we aren't actively probing, and this makes it safer and a bit more user-friendly. Now, if you do have any other suggestions on how I might handle this task in HAL, I am also all open to that. Because again, I'm kind of figuring out the Linux CNC stuff as I go along. I am a novice expert, trying to teach other novices to help bring us all to the level of novice expert. Simply because YouTube here doesn't have that much information on the topic, and I'm trying to spread what I learned. Because learning this stuff, it took months and months. It's not easy to learn. So I'm taking weeks of my time to take months of knowledge and condense it into hours of video to hopefully save you guys, months and months of time. But we'll call that a wrap for this video. Please do, like, comment, subscribe, all that crap if you enjoyed it, and do share it with your friends so that other people can learn this stuff too without going through all this nonsense on your own. Anyway, I'll catch you in part 7 now. We're finally going to hook up a Torch High Controller component to give ourselves a bit more control over the Z as the Plasma Torch is actively running. Until then, peace.